So yeah, hello everyone. A very good evening. So I hope I'm audible and visible. So I'm audible and visible. Can you confirm it? So let's wait for a few more minutes so that everyone can able to join this session. Okay, so no issues. You can go and check. There is a YouTube video. Video is also available for the last week now, so you can see from there. Yes, sure, I will post it here. So let me. This is a YouTube link for the first week. You can go and just check it. Otherwise, you can just go in the Swayam portal as well. There's a live and interactive session. There is a one sheet where the all the materials as well as the YouTube links will be there. So you can just see and check from there also. Hello. Yes, it's audible. I think it's audible now. Yeah. Okay, so let's start the session now. Okay, so hello everyone. A very good evening to all of you. So yeah, my name is Pooja Verma. I'm PMI Research Scholar from IIT Kharagpur, and the course instructor for this course is Dr. M.K. Bhuvan, Department of Electronics and Electrical Engineering, IIT Guwahati. This is a week 2 live and interactive session on computer vision and image processing fundamentals and applications. Okay, so I hope all of you have gone through this week video lectures. So already we have seen it. Yes, this is our course layout. So in the week 2, we will see some conceptual and numerical problems on the fundamental concepts of image formation. So yeah, these are some references and textbooks you can follow. And let's move on the questions for this week. So I hope I'm audible and visible. If not, any one of you can confirm it. And also, you can use chat box for interacting and asking your question. And otherwise, you can also unmute yourself and ask your doubts and questions. Okay. And please, during the live session, try to interact and give the answers. Okay, so this is the first our first question for this week. What is a general form of 2D shares transformation matrix in both x and y directions? So these are the options. Which option can be a correct one? Okay. So, yeah. Okay, D. Okay. Okay. So anyone else who want to answer this question? What is a general form of 2D CL transformation matrix in both x and y directions? Okay, so let's see the detailed solution for this one. Yeah. Okay, let's see, Devasmita. Okay, so many of you answered it. So let's see. Okay, so the solution for this question is the general form of 2D CL transformation matrix in both x and y direction is typically represented in the homogeneous coordinate as a 3 cross 3 matrix. We can represent in non-homogeneous coordinates as well. So how we can represent in non-homogeneous coordinates? So if we remove the last one because it is a 2D CL matrix, so it is represented in the homogeneous coordinates. So that's why it is a 3 cross 3 matrix. Otherwise, in the 2D form, it is a 1 SHX, SHY, and 1. So this matrix will allow for both x and y direction sharing to be applied simultaneously. Okay, so this is the correct matrix for the 2D Sear transformation matrix in both the directions x and y. And here SHX is the Sear factor in the x direction and SHY is the Sear factor in the y direction. Okay, so which option can be a correct one? So yeah, option D is the correct one. So option D is the correct answer for this question. Is it fine? Yeah, for the 2D, when we solve the problem based on that, in that case, it is a, it depends. It is they are asking whether it is a homogeneous form or non-homogeneous. So most of the time we will represent in the this type of MC type question, MCQ type question in the homogeneous form only. So it is a general form. Okay. Okay. So now moving to our next question. Which transformation uniformly alters the size of an object while preserving its shape and orientation? Okay, already answers coming so fast. Okay, others, please try to answer. Okay, option A, killing. Okay, okay, Divya. So yeah, most of you have given answers. So now moving to our answer or solution for this question. So option A is the correct answer. Yes. So scaling is the transformation that changes the size of an object. That uniform scaling increases or decreases the size proportionally in all the dimensions, which also preserves the object's shape and orientation as well. While in the translation, move an object one position to another position without changing its size, shape, or orientation. And in the sharing, what we are doing, that transform the skew and distort the shape of an object. While in the other rotation, that turns an object around the fixed point. This changes the object orientation but not shape and size. So yeah, scaling is the perfect and match for here. So option A is the correct choice. That is a scaling that preserves both shape and as well as orientation. So yeah, option A is the correct answer for this question. Okay. So now moving to our next question. Our next question is like these matrix equations are given. What is the matrix M for orthographic projection? The it is given E x y z is equal to M x y z 1. What is the matrix M for orthographic projection? Okay, options. Okay, C and A options are coming. Okay, any anyone else? Which option can be a correct one? Okay, so let's see the solution. So in the orthographic projection that maps a 3D point that is x, y, z onto a 2D plane, that is in the 2D plane typically the z plane is 0 by simply discarding the depth information that is a z coordinate and the rays of the projection are parallel to the z axis. So the equation that is given E is equal to mp where the input p is the homogeneous coordinate points that is x y z 1 and the output E is the three element vector. Okay, that is a representing 2D points in a homogeneous coordinate. So the matrix multiplication that is performed that for the new points that is x dash 1 into x or for y dash 1 into y simply we are multiplying by the 1. Okay, so the correct answer for that if you are getting for orthographic projection that is this one. This matrix 1 0 0 0 0 1 0 0 0 0 0 1. Okay, so yeah, option C. This one is the correct answer for this question. This is the orthographic projection for this equation. Okay. Okay. So now this is our next question. What is the primary characteristics of an affine transformation matrix? So option A, it preserves angle but not distances. Option B is it preserves parallelism and ratios of distances. Option C, it preserves only translation or it applies non-linear transformation. Which option can be a correct one? Yeah, Ninad, you can unmute yourself and whatever you want to ask, you can ask. Otherwise, you can just use chat box also.
Hello.
Yeah, yeah.
Ma'am, in the third question, um,
Okay,
in the explanation, uh,
okay.
the W component, is that is it because of you are making it into homogeneous coordinates or because the Z is zero, right?
Because we are projecting for the 2D point, like
Okay.
onto a 2D plane. It is a, for the auto, it is written a 3D point onto a 2D plane.
Oh, okay, okay, okay.
Yeah.
I see. Thank you.
Yeah. Yeah. So, Most of you have given the answer for the next question as well. For the yeah. So our next question was, what is the primary characteristics of an affine transformation matrix? Yeah, option B, most of you have given.
Option
Yeah,
B.
yes, option B. So let's see the detailed solution for this question is okay. Let me just enter some multiple. Okay, that affine transformation, which also include translation, rotation, scaling, and shading in the affine transformation. So that has a specific invariant properties. So the properties for the affine transformation is collinearity, that points on a lines remains on a line, and parallelism, parallel lines remains parallel after the transformation as well, and the ratio of length. If you have 3 points on a line, the ratio of the distances between them is preserved. So yeah, so the correct answer is option B. That is, it preserves parallelism and ratios of the distance.
Question 73.
Yeah, please. Who is it? Can you unmute yourself? I mean, mute yourself. So yeah, option B is the correct answer. It preserves the parallelism and ratios of distances. Okay. Okay. So now we are moving to our next question. When every entity of a geometric model remains parallel to its initial position, the transformation is called as translation, scaling, rotation, or mirror. Okay, you guys are too fast.
Yes, very good.
Nice. You're interacting as well and giving answers.
Screen 10.
Okay, A. Most of you have given the answer A. So yeah, let's see the detailed solution. A is the correct answer only. So the translation is a rigid body transformation where every point of an object is moved by a same vector d, and that object does not rotate, resize, or distort. So consequently, every line segment is transformed object remains perfectly parallel to the corresponding line segment in the original object. While we are also keeps lines parallel, the definition every entity remains parallel essential that describes the lack of rotation, which is defined feature of your translation. Okay, so yeah, option A is the correct answer. That is translation. When every entity of the geometric model remains parallel to its initial position, the transformation is called as a translation. Okay, so now moving to our next question. Now, next question is, for a given material, we are given by this equation. Yeah, okay, uh, let me just complete this question, then I will show. So, given by this equation, rho theta I theta r is equal to 1 by cos theta I, where theta is the angle made by the light direction with the surface normal, and theta r is the angle made by viewing direction with the surface normal. Can we use photometric stereo to reconstruct an object made of this material? Either yes or no. Okay, B, nice. Yeah, someone is asking, just show the previous slide. This one. Okay. So is it fine, Samina? Okay. So yeah. So, yeah. This is a next question. So please try to give an answer for this question. Okay. B. Okay. So let's see the solution here. So explanation for this question is the photometric stereolizes on a shading change, that is a change in intensity as the light direction changes to solve the for the surface normal. So standard redundant equation for intensity I is that is roughly denoted by this one. I is equal to rho theta I, cos theta I, and L intensity, where cos theta I is the geometric term, that is Limbert's cosine law, n into L, and if the material is VRDF, so the this function rho is 1 by cos theta I. So if we substitute in this intensity equation, so that will we get, and these two will be the cancelled out, and we will get I is equal to L intensity. So this result is constant intensity. So the image would look flat or no shading regardless of the surface curvature. So because the intensity does not vary with the surface normal, you cannot mathematically recover the surface normal, that is or shape from the image. So yeah, correct. Answer is no. So if we use the photometric stereo to reconstruct object, so we cannot use. Okay, of this material for this material. Okay, so now moving to our next question. So our next question is, which of the following describes the pinhole camera model? So option A is it uses the convex lens to focus light. It applies orthographic projection for rendering. Option C, it represents a 3D scene using perspective projection onto a 2D plane. Or option D, it captures images in 3D directly. Yeah, already answers coming. So yeah, option C. Okay. Okay. Option C. Most of you are giving answer. Option C is the correct answer. Okay. So let's see the solution. So a pinhole camera is the simplest camera model that light passes through a tiny aperture, that is pinhole, and projects as an inverted image onto an image plane. And mathematically, this maps 3D world coordinates, that is x, y, z, to a 2D image coordinates, that is UV, using perspective projection. So where objects further away appears smaller, that is division by depth. Yeah, this one is correct. It represents a 3D scene using perspective projection onto the 2D plane. Yeah, option C is the correct answer for this question. Okay, so now moving to our next question. Which of the following statements describes an affine camera but not a general perspective camera? Option A, an infinitely long plane can be viewed as a line from a right angle. Option B, approximates the human visual system. Option C, can be used to determine the distance from an object of a known height. Option D, relative sizes of a visible object in a scene can be determined without prior knowledge. Which option can be a correct one? Okay, option B. Okay, so let's see the solution or explanation for this question. So yeah, perspective camera. Just a minute, let me enter. Yeah, perspective camera for the objects scaled by 1 by z, that is depth. A small object close up can look identically to a large object far away. It cannot determine the relative physical size without knowing their depth. So in the affine camera or the orthographic or weak perspective, the projection lines are parallel, so there is no perspective for shortening, and the magnification is constant regardless of the distance. If object A appears twice as big to object B in the image, so object A is physically twice as big as object B. So relative sizes are preserved in the projection, which is unique property of affine or parallel projections compared to a general perspective. So yeah, correct answer is relative sizes of the visible objects in the scene can be determined without the prior knowledge. So yeah, option D is the correct answer for this question. Relative sizes of the visible objects in the scene can be determined without prior knowledge. Okay, okay. So now we are moving to our next question. Now, after I had actually today 25 questions, so we will solve some numerical problems in the later. First, just see the theoretically or conceptual question. Okay, options. Okay, so this is a question. Can you solve this one? So question number 9 is given as a convex lens produces a magnification of plus 1.4 for an object placed at a distance of 20 centimeter from the lens. The image distance and the focal length of the lens is. What will be the image distance and focal length? What is the formula to solve this question? Anyone? So here magnification is given and object distance is given. Okay. And for focal length, how we can calculate? Okay. Okay, so option C, most of you saying the option C is the correct answer. Okay, let's see. So here magnification is given, that is 1 minus, sorry, plus 1.4. That magnification we are representing here capital N, and the focal length you can represent by F. Already you know that is represented by F, and magnification, the formula for the magnification M is, yeah, you can use either di by du, where di is the image distance, right? Like it is the image distance, and the du is the object distance, right? Or you can also represent by this one also. Just a minute. V by U. Okay, final answer is A. Okay, so we will see which one is the final answer for this question. So here object distance U is given, that is du is given, right? So can you, any one of you tell that do or u, I can say that is 20 centimeter. So here why we will take this negative sign. So here it is given, a convex lens produces a magnification of plus 1.4 for an object placed at a distance of 20 centimeter from the lens. Okay, so here we will take the negative sign because it is the opposite side of the light propagation, because it is a convex lens. Okay, so here it is a 1.4 first V, and here it is a 20 centimeter. So here we are taking because it is a opposite side of the lens. It is a convex lens. Okay, so if you calculate, so here you will get the 14 into minus of 20. So you will get minus 28 centimeter first. Okay, so it is a convex lens. So just see whether it is a opposite side or in the side from the lens. So here we are taking minus sign because it is the opposite side of the light propagation. Okay, so now next, to calculate the focal length f, that already you know the formula in by v is 1 by u. Just yeah, positive J magnification is a virtual image. That is a correct. Okay, so if you now calculate the 1 by v is like minus 1 by 28, so minus sign will be there, and minus 1 by u, here it is also because it is opposite sign, so here we are taking the minus sign. So here you will get minus 1 by 28, sorry, here it is and here 1 by 20, right? Now I'm just calculating here. So here overall, if you take the LCMs overall, how much? 140, and here minus 5 plus 7. Overall, you will get 2 by 140. So here I'm just writing 1 by f. Finally, you will get 1 by 70. Okay. So here focal length we will get 70 centimeter, and the image distance you will get minus 28. Okay. So actually here none of the options are the correct. So here are some mistakes in the options. So the final answer, the image distance is minus 28 centimeter, that is V, and focal length is 70 centimeter. Okay, for this question. We are taking the here the U object distance is negative because it is a opposite direction from the light. Okay, just check with the convex and concave lens, that one, then just proceed with that one. And here the solution is also given for this one. So whether light travels left to right or right to left. Okay, convex or convention. Image distance that we have got is a minus 28. Okay, so yeah, already you guys started answering for the next question. Okay, so our next question is, which surface obeys the law of reflection? Option A is specular surface. Option B is normal surface. Or option C is Lambertian surface. Or option D is diffuse surface. Okay, option A. Most of you are giving the answer for option A. Okay. Okay, so let's see the solution for this one. So the law of reflection specifically states that the angle of the incidence that equals an angle of reflection, that is a theta I is equal to theta r, and that the incident ray, normal and reflected ray lie on the same plane. So in a specular surface like mirrors or smooth metal, exhibits the behavior perfectly, and in the diffuse and Lambertian surfaces, scattered light in all the directions, which the results of a rough geometry at a microscopic level that effectively breaking the microscope law of reflection for the observer. Okay, yeah, so correct answer is specular surface. A is the correct answer for this question. Specular surface obeys the law of reflection. Okay, okay, so now moving to our next question. Which of the following best describes the Lambertian surface? Option A, its surface where radiance depends on the illumination direction. A surface where radiance leaving the surface is independent of the angle. Or option C is a surface that only reflects light in a single specular direction. Or option D is a surface where BRDF varies significantly with the viewing angle. Okay, most of you are giving the answer B. Okay, so let's see the detailed solution. Here it is given. So a Lambertian surface is an ideal matte or perfectly diffuse reflector that exhibits isotropic luminance. That means the radiance, that is the brightness as perceived by an observer, is the same regardless of the viewing angle. So while luminance intensity emitted from the point on the surface follows that Lambert's cosine law, decreasing as the cosine of the angle from the surface normal. The perceived area of the point decreases at the same rate. That results in the constant radiance. So why the other options are not correct? So here it is given. So option A is a surface where radiance depends on the illumination direction, while the total amount of the light reflected, that is the irradiance, depends on the angle of the incoming light. That defines the characteristics of the Lambertian surface is the independence of its outgoing radiance from the viewing angle. Our next option is option C, that is the surface that only reflects light in a single specular directions. That describes like a specular or mirror-like surface, which is a fundamental opposite to the Lambertian surface. And our option D is a surface where the BRDF varies significantly with the viewing angle. For the Lambertian surface, the BRDF is constant value. Okay, so the correct option is option B, a surface where radiance leaving the surface is independent of the angle. Yeah, option B is the correct answer to describe the Lambertian surface. Okay, so now moving to our next question. In a Phong model, what effect does a large value of a specular exponent n have? Option A, it produces a wider specular lobe. Option B, it results in ambiguous boundaries for the specularity. Option C, it produces a small and narrow specular lobe or sharp specularity. Option D, it increases the diffuse component of the surface radiance. Which option can be a correct one? Option C, okay. Okay, C only, okay. In the Phong model, the effect does a large value of the specular component n have. Okay, so let's see the solution for this one. So in the Phong deflection model, the specular component, that is a n, is also called a shininess factor or specular power. That determines the concentration of the specular highlights, and the model calculates the specular intensity as the proportional to R into V to the power n, where R is the reflection vector and V is the view vector. So if the large values of n will occur, so because of the dot product of R into V is the value between 0 and 1, that raised it to its higher power causes the intensity to drop off that much faster as the viewing angle derivative deviates from the ideal reflection direction, and that results small, tight, and sharp highlights that simulating a very smooth or shiny surface, like a polished mirror of metal. Okay. The other options for the this one is it produces a wider specular lobe. So a wider specular lobe is produced by a low values of n, not a higher values of n. So when n is small, the intensity decreases slowly, and that might make highlight appear larger and more spread out. And it results the ambiguous boundaries for the specularities. So high value of n actually make the boundaries of the specular highlights more distinct and sharp, whereas low values make them looks blurry or dull. So it increases the diffusion component of the surface radius. So the specular component n only affects the specular term of the Phong model. So the diffuse component is controlled by a separate constant, that is a Kd, and the angle between the light source and the surface normal, that is n into f. So it is independent of n. Okay. So yeah, option C is the correct answer. It produces a small and narrow specular lobe, that is a sharp specularities. So yeah, option C is the correct answer. In the Phong model, the large values of the specular component produces a small and narrow specular lobes. Okay, so now we will move to our next question. What is the minimum number of images usually required for a standard photometric stereo to recover surface normal? Option A 1, 2, 3, or 5. What is the minimum number of images usually required for the standard photometric stereo to recover surface normal? A. Option B. So, others, you want to answer for this question? What is the minimum number of images that is required for the standard photometric stereo to recover surface normal? At least try for this question. What will be the correct answer? Okay, we will see whether option A or B is correct. Okay. Okay, so let's see the solution here. So in the standard photometric stereo, typically minimum three images uniquely determine the surface normal at each pixel. So this requirement stems from the fact that Lambertian surface, there are three unknown to resolve: the albedo, that is surface reflectance, and the 2 degree of freedom for the surface normal vector. These are the three unknown to resolve. Okay. So by using the three different light source directions, a system of three linear equations is formed and which can solve these variables. So yes, option C is the correct. We need three to solve the surface normal at a point. Photometric stereo, that is typically uses the least three images taken from the same viewpoint under different lighting conditions. So why the other options are incorrect? One, a single image is used in a sharp shape from shading, which is generally an ill-posed problem and cannot be uniquely recover surface normals without significant additional constraint. Or option B is two, while some modern techniques can estimate normal from the two images by assuming known albedo or using specific integrability constraint. This is considered a degenerate or immediate case rather than a standard approach. And five, although using five or more images creates over-determined system that can improve accuracy by handling shadow or specularities, it exceeds the minimum mathematical requirement for the standard recovery. So correct option is three. We are required the three to solve the surface normal for the standard photometric stereo to recover surface normal. Okay, so option C is the correct answer for this question. Yeah, we will upload this one after taking this class in the YouTube. Okay, all these topics are covered in week one. Are you asking or just telling me? So here some questions may be included from the week one, but most of the questions have been taken from the week two. Okay, so now moving to our next question. So how is the translation operation represented systematically in a 2D homogeneous coordinate system by a 2 cross 2 matrix? It is symmetrically. Okay, how is the translation operation represented symmetrically in a 2D homogeneous coordinate system by a 2 cross 2 matrix? Option B, by a 3 cross 3 matrix with a translation vector in a third column. Or option C, by a 2 cross 3 matrix. Or option D, by adding a vector to the original point coordinate. Okay, option B or D. Okay, so all these topics I think this is not covered in our week one. This is a for week two only. Okay, okay, option B. Okay, so let's see the solution here. The explanation is given here. So in a 2D Cartesian system, the translation is performed by adding a vector to a point like this: x dash is equal to x plus th and y dash is y plus th. So this is a affine transformation that cannot be represented by a simple 2 cross 2 matrix. Okay, so to represent the translation in a matrix multiplication, we use homogeneous coordinates and which add a third dimension, typically set at 1 for a point, and this results 3 cross 3 matrix that allow for the composition of the various transformation, that is rotation, scaling and translation into a single operation. So the in a general 2D translation matrix T to the translation vector that is a Tx Ty that is represented. This is a new points and this is a existing point and this is our matrix that is a translation matrix. So the key components for this matrix is identity block that is at the top left 2 cross 2 portion that is this one that ensures no scaling and rotations occur, and another one is a translation vector that is Tx and Ty, that is Tx is in the x coordinate and y is in the y coordinate. The values of Tx and Ty that are placed in third column first two rows, and in the homogeneous rows that is the third row that is 0 0 1 to maintain the homogeneity of the coordinate. So yeah, option B is the correct answer by 3 cross 3 matrix with the translation vector in the third column. So yeah, option B is the correct answer for this question. Okay, okay. So now moving to our next question. So next question is which transformation is occurring if a square is distorted into a parallelogram but its base and height remains unchanged? Option A, uniform scaling. Option B is rotation. Option C is shearing. And option D is reflection. Which transformation is occurring if a square is distorted into a parallelogram but its base and height remains unchanged? Okay, so option C, most of you are saying that. Okay, so let's see the solution. Here, there are different. Yeah, sharing is the correct answer for this question, but we will see the other options what is exactly. Okay. So first one is uniform scaling. So in the uniform scaling, that transformation changes the size of the object by enlarging or shrinking it in all the directions proportionally. So it preserves the shape and the square remains I square and the internal angle, but it does not change both base and height. Okay, in the uniform scaling because we are scaling in both the directions. And in the rotation, so rotation involves the turning the figure around the fixed point. So it is a rigid body transformation. Already we have seen that. That means preserve the size, shape, and angle of the object. So the square will remains the square. It does not change any orientation. It just change its orientation. Okay. So in the shading, what it is also known as a screen. So it is a linear transformation that trends a shape of the object when we apply a square to shift the coordinate of a point in a specific direction. Either it is horizontally or it can be a vertically. So it become a parallelogram. So while it keeping the original area and its weight side dimension constant. So for instance, if we x here shift, that is x value we shift and their y position based on their y position. So it effectively tilting the side while the base and height remains exactly as the same. Okay. And the reflectance already, this is not related to this one. So this create a mirror image of the object across the specific like rotation or its rigid body transformation that preserves length and angles of the square. That means does not distort the into a parallelogram. So yeah, option C is the best match for this question. Just a minute. Okay, so sharing transformation is occurring if the square is plotted into a parallelogram, but its base and height remains unchanged. So option C is the correct answer for this question. Okay. Now, our next question is related to a pinhole camera model. So, in a pinhole camera model, why should the aperture not be made as small as possible? Option A, it would cause too much blurring. Option B, it would lead a significant diffraction effect. Option C, it would increase the depth of the field too much. Or option D, it would make a image inverted. Okay, option B. So our question is, in a pinhole camera model, why should the aperture not be made as small as possible? Okay, so let's see the solution here. So option A, our A is it would cause too much blurry, right? So while we can make a hole too small, does cause blurring. So this is a symptom of the diffraction rather than underlying this reason. So in the standard multiple in this question, option A usually refers geometric blurring, that is caused too large or not too small. Then option B, in a pinhole camera, the aperture should not be made as small as possible because the hole size decreases, light begins to behave more like a wave than the straight ray. So this phenomenon known as a diffraction causes light to bend or spread out or passes through the narrow opening. So while a smaller hole initially sharpens the image by reducing the geometric blur or circle of the confusion. So once hole becomes too small, the spreading causes diffraction over weight. This benefits but makes blurry and unsharp again. So our option C is it would increase the depth of the field too much. So a small aperture actually increase the depth of the field, which generally desirable features of the pinhole camera, and also as a sight as a infinite or depth of the field. So this is benefit, but not a reason to avoid making hole smaller. And our next option was that it would make an image inverted. So pinhole images are always inverted regardless of the aperture size. So this is a not a fundamental. This is a fundamental property of the geometry, not a reason limit how small the hole is. So our best correct option is option B. It would lead a significant diffraction effect. Okay, it would lead a significant diffraction effect. So option B is the correct answer for this question. Now, our next question is according a thin lens equation, that is 1 by d naught plus 1 by di is equal to 1 by f, what type of image is formed when the object distance do is less than the focal length? Option A is a real inverted image. Option B is a real upright image. Or option C, a virtual image. Or option D, no image is formed. Which option is correct for this question? So this one is a lens equation. Already we know that. So what type of image is formed when the object distance, that is 3 naught, is less than the focal length f? Okay, so most of you saying that is C, option C. Okay. Okay, someone is saying option A as well. Okay, so let's see the solution for this one. So already we know that this is our thin length equation. 1 by d naught plus 1 by di is equal to 1 by f. So this equation that is determine the nature of the image. We can rearrange the formula to solve the reciprocal of the that di. This one we can arrange like this, right? 1 by d I, if we take this side, so this equation becomes this one. So here we are given that the object distance is less than the focal length, right? This one d naught is less than f. So when denominator is smaller, the overall fraction is larger. So therefore, this one by d naught must be greater than 1 by f. If we just take the denominator in the reciprocal. So by substituting in this our equation, 1 by d naught is here greater than 1 by f. So the result will be the 1 by f minus 1 by d naught must be a negative number in that case. So that means di is the negative. So in optics sign convention, the negative image distance, that is di, if less than 0, that indicates image is formed on the same side of the lens as the object. So this type of image is defined as a virtual image. Okay. So yeah, option C is the correct answer. Virtual image will be made if the object distance is less than the focal length. Okay. If di is negative, that is a virtual image will form. Okay. Yeah, option C. So have you understand it from here how it is? So I hope you have understand this question. Now moving to our next question. Now just two more, I think, theoretical questions will be here. Then we will solve some numericals as well. So how does aperture size affect the depth of the field in a camera? So option A is a larger aperture increases the depth of the field. Option B, a smaller aperture increases the depth of the field. Or option C, aperture size only affects image brightness, not focus. Or option D, depth of the field is slowly determined the focal length. So which option can be a correct one? Okay, most of you are giving answer. It is option B or D. Okay. So how does aperture size affect the depth of the field in a camera? Okay, so let's see the detailed solution here. Explanation is given here. So the aperture size and depth of the field. So there is a inverse relation between the physical size of the aperture and depth of the field. So as we decrease the aperture size or close it down, the depth field increases. Okay, so F stop confusion. One is it is important to note that the higher F number, that is F by, like F by 11 here example is representing the smaller physical aperture. Okay, so their practical use larger aperture, that is smaller F number used for a portrait to create the shallow depth of the field with a blurred background and a smaller aperture. That is, if F, F number is large, so if this is used for landscape to ensure entire scene remains sharp. So the other option, why incorrect? So a larger aperture increase the depth of the field. So this option is opposite of the optics work. So larger aperture widen opening creates a shallow depth of the field that results more background blur. Okay. So our next option C is aperture size only affect image brightness, not a focus. So while aperture does regulate the amount of light, that is the brightness, it also fundamentally controls the range of sharpness in an image. Okay, so in the depth of the field is slowly determined by the focal length. So although focal length does influence the depth of the field, it does not slow sole factor. Depth of the field is determined the combination of aperture size, focal length, and subject distance, as well as sensor size as well. So the correct option is B. A smaller aperture increases the depth of the field. In a photography, a smaller aperture, which corresponds to the higher f number, that is like such as f by 16 or f by 21, that creates greater depth of the field. That means more of the scene from the background to the foreground to the background appears in a sharp focus. So this occurs because of the smaller opening, narrow of the beam, and light reaching to the sensor. Okay, and that reduces the size of the circles of the confusion for the objects that are not at exact point of focus. Thereby, they that make or that appear sharper. Okay, so option B is the correct answer for this question. A smaller aperture increases the depth of the field. Okay, yeah. So option B is the correct answer for this question. So now moving to our next question. Our next question is a 3D homogeneous coordinate. How is a point XYZ represented? In a 3D homogeneous coordinate, how this point can be represented? So can you just, it is a very basic question. I think all of you know that. Yeah, option C is the correct answer. In a 3D homogeneous coordinate, the point XYZ is represented by the XYZ and 1. Okay, so by adding 1 in a 2D coordinates, it is a homogeneous coordinate representation. So here the explanation is given in a computer graphics or geometry. Homogeneous coordinates allow the representation and transformation like translation, rotation, scaling using the consistent matrix operation. So to convert the 3D Cartesian point to a homogeneous, an extra dimension W, that is also called W, we can add, and this point we can represent by this one also, or X, Y, Z, W also. Okay, and this is a standard form to simplify calculation by typically setting it 1. And vectors versus point, while point is uses W is equal to 1 to allow for translation, a vector uses W is equal to 0 because direction does not have position and should not be affected by a translation. So we can convert it back also by just dividing it by W. Already I think you know that. So the correct representation of the point XYZ to a 3D homogeneous coordinate is, that is XYZ 1. So option C is the correct answer for this question. Now we will move to our next question. Which projection model assumes the focal point is at infinity and rays are parallel and orthogonal to the image plane? Option A is perspective projection, option B is pinhole projection, or option C orthographic projection or radial projection. So which projection model assumes the focal point is at infinity and rays are parallel and orthogonal to the image plane? Okay, option C orthographic projection. Most of you are answering. Okay, so let's see the solution here. Which one is the option C is the correct answer for this one. But we will see the other projections as well. What is a perspective projection? So this model assumes rays converge at a finite center of the projection, like the eyes or the camera lens. That means ray is not a parallel. Objects appear smaller as they move further away. So this one is a perspective projection. The project perspective projection. The model already assumes that it is a finite center of the projection. And in a pinhole projection, already we know that this is a specific type of perspective projection where light passes through a tiny aperture or the pinhole from the inverted images. That rays are not parallel as they must pass through the single central point. Okay, and in the orthographic projection, so in the orthographic projection, the center of the projection focal point is assumed to be infinite, and this placement ensures that all projection rays like line of sight or parallel to each other to rather than converge at a single point. So that for the projection to be specifically orthographic or opposed to oblique, these rays must be a orthogonal or a perpendicular to the image plane. So this model is used in an engineering architecture drawing because it preserves a true dimension and eliminates perspective distortion. Our last projection is radial. So this usually refers to a projection that involves distortion or deals with the points radiating from the center. It does not assume rays are the parallel and orthogonal to the plane. So correct option is orthographic projection. That is a option C is the correct answer for this question. So which projection model assumes the focal point is at infinity and rays are parallel to and orthogonal to the image plane? This one is the orthographic projection. Okay. So here now we will solve some numerical problems. This is a basic numerical problems as well. So as you can see, here are the three questions. So can you solve with me? So here this is a basic questions as well based on the that is transformation matrix. So our this question is a point P is rotated by a 90-degree counterclockwise about the origin and then translated by Tx that is in the x direction 4 and y direction -1 using homogeneous coordinates, find the final position of the point. So can we solve this question? So how we can solve this question? This is a simple rotation, translation or matrix to find the new coordinates. So here a point is given and it is also given it is rotated by a 90-degree counterclockwise about its origin. And after that rotation, it is also translated by these points. Okay. And use the homogeneous coordinates. So after this many application, what will be the final position of the point? So can you calculate this question? Okay, so let's calculate it. Let's solve this question first. Okay, so first we need to represent the given point. So for question number 21, so given point P is 2 and 3, right? This one. Now first we need to represent it in a homogeneous coordinate. In homogeneous coordinates. So how we can represent it? Just by adding 1, right? Or the blue. It is a homogeneous representation of this coordinate point, right? Now they have told that and this point is rotated by a 90-degree counterclockwise. So what will be our rotation matrix? It is rotated by a 90-degree. So first we need to find out our rotation matrix to calculate the final point. So let's say it is a R. So it is rotated. So this is our rotation matrix, right? Cos theta, if it is a here minus sin theta 0, and here it is a sin theta again, cos theta 0, and here 0, 0, 1. So here angle theta is given, that is a 90-degree, right? It is given. So if we put here, so cos 90-degree minus sin 90, 0, sin 90, cos 90, 0, 0, 0, 1. So what is the value of cos 90? So are you solving it or not? Yeah. So just find out the values. So cos 90 is 0, sin 90 is 1, so minus 1 will be here, so 0. Again sin 90, so 1, 0, 0, right? And here 0, 0, 1. So this is our rotation matrix. Now similarly we need to find out our translation matrix as well. Translation matrix, that is T. So already it is given that the 2 points are given. So already we know that the matrix for the translation matrix, right? 1, 0, it is a Tx in the x direction, right? 0, 1, Ty already you have seen in the previous slide explanation, and it is also 0, 0, 1. So here Tx and Ty is given, right? Here Tx is 4 and Ty is minus 1. Okay, so just put in this 1, 0, 4, Tx is 4, 0, 1, it is a minus 1, and it is 0, 0, 1. Okay, so this is our translation matrix. Okay, so now I have to remove it from here. So have you noted down? Can I remove it from here? Solver next. So now first next step is to calculate the composite transformation. That is that we call composite transformation matrix, because we need to calculate the final point. So just we need to multiply all these matrix. So M, that is first we will multiply translation matrix and rotation matrix. So can you multiply these two matrices and let me know what will be the answer? So can I remove it from here? So I'm just removing it from here. I hope all of you have noted down so that we can just Okay, so which books already we have suggested in the third slide of this. So that is a standard books. From there you can take a questions. Okay. So first we need to calculate the composite transformation matrix, that is M, that is translation into rotation matrix. So our translation matrix is 1 0 4 0 1 minus 1 0 0 1, and our rotation matrix is this one. So 0 minus 1 0 1 0 0 0 0 1. So if you multiply, first multiply this row to this column, right? This row, this column, this row, this column, then here this. So if you just take 1 into 0 0 0 into 1 0, and 4 into 0. So in the first you will get 0. Now first row, second column of this matrix, this one. So here you will get 1 into minus 1 1, and all the, so minus 1, and similarly here 1 into 0 0 into 0 4. So in this you will get 0 minus 1 4, the first row. Similarly you can calculate to the next. So second row, first column. So here in this place is 1. So 1, here 1, here you will get 0. Now next here you will get minus 1, right? Similarly for the third row, first column, you will get 0. Similarly the next also 0, and in the third place, I mean 1. Okay, like third row and third column. So this is our composite matrix. So M. So now next, to calculate the final point, to calculate the final position point is like, let's say it's P dash. So P dash is M into P, and this is M, and P already we have seen that. I'm just removing it from here. So just multiply this matrix to a 0 minus 1 4 1 0 minus 1 0 0 1 to a given point, that is 2 3 1, right? Now if you just calculate, so overall you will get the final position of a point. So first row, this column, right? This first one. So 0 into 2 0, minus 1 into 3 minus 3, plus 4, right? Now next, this row to this column. So 2 plus, it is a 0. So sorry, here it will be the minus 1 because it is minus 1. Now next one is 0 0. So 1 here only left. So here you will get 1 1 and 1. So final position point then is 1 1 1. So if you again just convert it homogeneous to non-homogeneous, or you can say 3D to 2D coordinate. So if you just divide, the final position point is 1 1 1. So if you just again divide in the 2D coordinate, so you will get 1 and 1 only, because if you divide 1, so you will get finally the 1. So the final position point or new coordinate is 1 1. Okay, here the final position point is 1 and 1. This one is the answer for the 21. Okay, now next question is, an object is placed 30 centimeter, that is a D naught, in front of the, here it is written, in front of the thin convex lens with a focal length f is 10 centimeter. Now we have to calculate, first one is calculate the image distance di, determine the magnification m, and is the image is virtual, real or virtual. Can you tell me. So is it fine? Question number 21 is fine. Have you understand this question? Is it okay? Can we move to our next question? Anyone? Can we move to our next question? Okay. So now we will solve the next question. That is question number 22. I'm just removing it. Okay, someone is saying no, only two numbers in the last step. Yes, because we are converting it to a 3D to 2D plane. Already we have converted in a homogeneous equation, right? Only 2 points are given, that is 2, 3. Then we have added the 1 to convert it into a homogeneous coordinate. So again, we will convert it back in a non-homogeneous coordinate. That means in a 2D plane. That's why 2 points are there. Okay? Okay. So here I'm removing it. So can you solve for the next question 22? It is based on the lens equation itself. We have solved it, that type of problem previously. And let me know what will be the answer for that question. Is it 22? So here it is a this type of question we have solved. An object is placed 30 centimeter, that means object distance given, that is a 30 centimeter, and focal length is also given, that is a 10 centimeter. Now we have to calculate the image distance, magnification, and also tell is the image is real or virtual. Okay, so already we know that using the thin lens equation to solve this problem, use thin lens equation. So this is 1 by f is equal to 1 by d naught, that is the object distance, and 1 by di, that is the image distance, right? Okay, someone has answered as well. Okay, okay, Murthy, right. So just here it is a given, the given values f, that is a focal length, right? This is a 10 centimeters it is given, and the object distance, that is d naught, is given 30, right? Uh, yeah, 30 centimeter. So now put in this equation and get di. So 1 by di is equal to 1 by f minus 1 by d naught, right? So just put all the values, 1 by 10 minus 1 by 30. So 1 by di is equal to 30. So 3 minus 1, we will get 2 by 30. Overall, we will get 1 by 15. So the image distance di is 15 centimeter. Okay, we will get. Now to calculate, this one is a first, this one is the second part of the question number 22. So to calculate the magnification, so what is the formula to calculate the magnification? magnification M, that is di divided by d naught, right? That is, it is the image distance, it is the object distance, right? So here it is a given an object is placed 30 centimeter d naught in front of the thin convex lens. So it is a object is placed in a front of the thin convex lens. So that means the image this image will form where it is a after the convex, so it will be the minus sign will be there, right? Because the image will form the opposite side. Already we have seen in one question, right? Why we are taking the negative sign? The image will form in the negative side, so that's why here we will take the minus of di. Okay, so here minus 15 divided by d naught is given 30 centimeter. So again minus 1 by 2, right? Or you can say minus 0.5, right? So that means the image is half of the size of the object, right? From here we can say that because image size is 15 centimeter, object size is 30 centimeter. So is it fine? So here M is a negative sign. That means the image is a virtual, right? That indicates and that so the nature of the image is determined by the sign of the image distance, right? Since pi is a positive here, for calculating magnification we are taking the minus sign, but otherwise we have got ti is 15 centimeter. That is a positive. Okay, that's why it is a here it is a virtual, right? So di we have got 15 centimeter and it is minus 1 by 2 and it is a virtual image. Is it fine? Can we move to our next question? Okay, so next question is a 3D point that is a x, y, p, x, y, z is given 10, 20 and 100 is projected onto an image plane using a pinhole camera model. The focal length that is a distance from the center of the point to our image plane is f is equal to 50. Assuming the center of point is at origin and camera looks along the z-axis. Now we need to find the projected image coordinates that is a u and v. So how we can find out the projected image plane? A 3D point is given 10, 20 and 100 that is projected onto an image plane using the pinhole camera model. And focal length f is also given that is a 50. Now we can assume that COP is at the origin and camera looks along a z-axis. Now we need to find out the projected image. So let's solve this question here. Is it fine to all of you? So now we are moving to our next question, that is 23. Okay, so as already we know that in a standard pinhole camera model, where the center of the projection is at the origin, right? Here it is also given center of the projection is at origin. That means 0, 0, 0, and the camera looks along the z-axis towards an image plane. At that means z is equal to f. So the projection of the 3D point xyz onto a 2D plane ub is governed by a similar triangle. So the projection equations are, can you tell this one? What are the projection equations? The projection equation is calculated by this one, f x into z, and the next coordinate f y into z, right? On already the point P, that is x, y, and z values is given as 10, 20, and 100, right? And also focal length f is given 50 centimeter. Now in the projection equation we can put and find out the new points, that is the u and v, or you can say that projected image coordinates. Okay, so just put in these two equations what will be the value. Now substitute these values and calculate the horizontal and vertical coordinates, that is a u and v. So just you can put f is given 50, x, this one is our x point, x, y, and z, right? So x is 10 and our z is 100. So if you just calculate it, you will get e is 5, and v is equal to, here again 50 into y is 20, it is given 20 by 100, so it is 10. Okay, so the projected image coordinate is image coordinates u and v are, that is 5 and 10. Okay, is it fine? How to calculate it from this projection equation? Is it okay? Can we move to our next question? Okay, so now moving to our next question. So yeah, our next question is, in a photometric stereo setup, a Lambertian surface point has an LRO, that value rho is 0.8. Three light sources are used with the directions L1 is 100, transpose L2 is 010, and L3 it is L3 is 001. The measured pixel intensity are I1 is 0.4, I2 is 0.4 again, I3 is 0.566. Now we need to find the surface normal n, that is nx, ny, and nz at that point. So here a small, the given, what is a Lambertian surface and reflectance equation, how we can calculate. So already I think you know that for the Lambertian surface the intensity I is recorded from the light source Li, that is given dot product of the light direction and the surface
சரி,
normal.
அத போட்டு என்ன பண்ணீங்க? நீங்க காலையில
So
போயிருப்பீங்கல்ல,
note yourself.
அது அங்கேயே வச்சுங்க.
So this is the equation for the Lambertian reflectance surface. So II is rho Li transpose n. Okay, and where n is the surface normal, this one, and this one is a light source, and light source matrix, that is L1, L2, L3, or Ln, L till Ln. So here only three values are given, so that's why I 3 cross 3 matrix in that case. So three values will be there, I1, I2, I3. Similarly for this one. Okay. So now we need to calculate an x and y and n z for this one. So already all values are given. Like rho is given, that is 0.8. L1 is given. For the 3 only we have to calculate an x, y, z. So L1, L2, L3 given. I is also given, that is this part is also given. This one is given. So now we can calculate this one, right? Okay, so let me take right for the 24th number of question. So let's first write the given values. So given rho is given 0.8, I1 is equal to I2 is given 0.4, I3 is given 0.566, right? Yeah. So already we know that the Lambert equation rho Li transpose and n, like n within the bracket n, or and n represents the nx and y and z transpose, right? Okay, so let's first we will calculate for I1. So I1 will be the rho L1 transpose n, or we can say that rho L1 transpose, let me write nx, ny, and nz, right? In that form, because we need to calculate. So just put for to calculate. So I1 is 0.4, rho is 0.8, and L1 transpose, that is already given, that is 100. Here it is 100. So here it is transposed, and now nx and y and z. So if you multiply these two first, so here we will get nx, and all ny and nz will be the 00, right? If you multiply this one, so nx 1 into nx, so 0.8 nx, and here 0.4. So directly we can calculate here 0.4 divided by nx, 0.8, right? 1 by 2 or 0.5. So nx we have got 0.5. Similarly, we need to calculate for I2. So rho L2 transpose n, or you can say that rho L2 transpose L2 transpose nx and y and z. Just put all the values. I2 is also again 0.4, rho is 0.8, L2 is yeah, 0, 1, 0. So 0, 1, 0. Now again just multiply with this one, ny and z. So here you will get 0.4 is equal to, here this nx will be 0 and z will be 0. Here only left 0.8 ny. So again ny you will get 0.5. Okay. Now similarly we need to calculate for nz. Okay. So again the next will be, so can I remove from here this side, the upper side? Can we remove to calculate the nz value? Till now it is fine for you? Okay. So I'm just removing it with this one. Already, I hope all of you have noted down. The nx and y are the same. So 0.5, 0.5. Similarly, we can calculate for, so I can write nx, we have got 0.5, and y we have calculated again 0.5. Now similarly, we can calculate for I3 also. Rho L3 transpose n. So I'm directly writing nx, ny, and nz. So I3 is 0.566, rho is 0.8, it is given. L3 value that is given 001, right? 001. Similarly, we can calculate nx and y and z. So again, if you see that this part and this part and x and y coordinates will be 0, 1 and z only. So 0.8 and z, here 0.566. So again, nz we can calculate 0.566 divided by 0.8. So if you just divide it, you will get approximately 0.707. Okay. So nx, ny, and nz that we have got 0.5, 0.5, and 0.707. Right? So the normal surface n is nx, ny, nz transpose. It is given in this equation, that is n. So that is our the final answer, 0.5, 0.5, and 0.707 transpose. This is a normal surface. So this one is a final answer for this question. Is it fine? Okay, so now moving to our last question, last and final question. Okay, so yeah, now next question is, we have seen one theoretical question in this. Now we will solve the numerical problem on this. So here a unit square with vertices 0, 0, 1, 0, 1, 1, and 0, 0 undergoes a shear transformation with hx is equal to 2 and hy is equal to 0. Now we need to find out the new coordinates of the vertices. So these points will undergoes through the shear transformation, right? So already we have seen that a 2D shear transformation matrix, right? That is defined by the shear factor, that is hx and hy. Hx is the horizontal coordinate and hy is the vertical coordinate. So that one very first question. So the shear matrix that we can define, shear matrix equation. So you know that 1 into hx hy into 1. Here it is in a 2D coordinate, so why this is we are taking, and here we are not going to the homogeneous equation. Otherwise, that will be the 3 cross 3 matrix, and that will be the very large. Now we need to convert again all the into the homogeneous coordinate, and that multiplication will be the lengthy and large. So here directly we are taking the 2D coordinates only, 2D points. Okay, that's why we are taking the 2 cross 2 shear matrix. So just put the all the values. Here hx is given 2, hy is given 0. So just put, so you will get the shear matrix, right? Now we need to find out the new coordinates of the vertices, right? So to find the new coordinate of the vertices, first we need to multiply the shear matrix by the each vertex vector. Okay, just I'm writing to find the new coordinate that is x dash and y dash, we need to multiply the here matrix with each vertex vector to find out the new coordinate. So the formula will be x dash y dash 1 2 0 1, the original coordinates like this, the unit square coordinate. So we need to find out the all the coordinates. So just multiply with the each coordinates. Okay. So I'm just removing it from here. I hope all of you have noted down. So multiply each point. So first point for vertices is for vertices 0 0. So just put in this one for 0 0. We will get 1 2 0 1 0 0. So what we will get here? All the values will be 0 for the vertices 0 0. So we will find the same coordinates. Now second is vertices, that is 1 0. So again put 1 2 0 1 1 0. Here what we will get? 1 into 1 0. So 1, and in this side 1 0. We will get the same coordinates for this one. Now for the vertices 1 1, what the new coordinates will be? 1 2 0 1. Here 1 1. So in the upper one we will get the 1 into 1 1, 2 into 1. So 3 1. So the new coordinate will be the 3 1 for the vertices 1 1. Now similarly we need to calculate for the last vertices. So vertices 0 1, similarly for that one 1 2 0 1 0 1. Here what we will get? In the upper x direction we will get 2, in the downward we will get 1. So these are the 4 new coordinates for the each vertices. So the new coordinates of the vertices are, first one is a 0 0, next one is a 1 0, that is same, the third one is a 3 1, and last one is a 2 1. Okay, so just I'm removing it from here. I need that much of a space. So the new coordinates I'm just writing here again. New coordinates are for each vertices, that is 0 0. Next one is a again same. This is a 1 0. Third one is for third one 3 1, and for fourth one it is a 2 1. Right? So these are the new coordinates. So if you observe that already we have unit square with these vertices. So here the square became parallelogram, right? With the same area, but the top angles is shifted, these two shifted by a 2 units to the right. Okay, so this is a parallelogram effect that we have seen. One. Is it fine? Have you understand this question? That is related to that parallelogram that we have seen in the one is theoretical question. So how the edges got shifted by using the shear transformation. and that will create with the same area. Okay, so this is the last question for this week. So yeah, thank you everyone. Thank you for joining this session. So if you have any doubt, you can ask. Otherwise, we can close the session. Okay. So if you don't have any doubt, so you can leave the session. So yeah, thank you everyone. Thank you for joining this session. Yeah, already I have shared in the chat box. Yeah, just a minute. I will share it again. Yeah, this is a for first week video. So use the standard book itself, standard writing book. Already it is given in the first slide, so you can just check with this slide. Okay, just a minute. Yeah, some text and references are there. So you can use mostly reserved this one, third one. This is a standard book for the computer vision. And for image processing, this is Gonzalez is the main. Okay, so yeah. Thank you everyone. Thank you for joining this session. Now I'm closing this session. Anyone have any doubt? If you don't have any doubts, so just you can leave this session. Okay, everyone. So thank you. I'm just closing this session.